Hello, and welcome to tonight's edition of Pint of Science. After over a year of not straying far from home, tonight we'll be taking you out of this world in an evening of space exploration. First off, I want to give a massive welcome to everyone who's joined us live tonight on our live stream, and a further welcome to everyone who's watching this back on YouTube. We've got two fantastic speakers lined up for you tonight, as Dr. Ziri Younsi and Divya Persaud will guide us through the fascinating world of space imagery. My name is Ledden, and I'll be your host for tonight. For anyone who hasn't attended Pint of Science before, you're in for a treat. Basically, we've got two super brains who are experts in the area of space imaging, and they're going to dumb it down for us while we sit back, have a drink, and enjoy the science. The rundown for tonight's event is that we'll start with our first speaker, Dr. Ziri Younsi, who'll be talking about his work as part of the Event Horizon Telescope team, who's first successfully imaged the supermassive black hole. Following that, we'll have a short break for you to grab a drink, during which time I'm going to force our speakers into some public small talk with me for your entertainment. Then we'll return for our second speaker, Divya Persaud, who's going to talk to us about her work using 3D imagery to study the geological history of Mars. After both of those, we'll open up for a Q&A between the two speakers with questions from you. So throughout the show, you can pop your questions in the chat, and our YouTube moderators will also be talking to you throughout the show, so keep them busy by talking to them in our YouTube chat. You can also let us know your thoughts on Twitter using the hashtag Pint21 or tagging us at Pint of Science. Okay, that's enough from me. Let's start the show. Our first speaker tonight is Dr. Ziri Younsi. Ziri is an astrophysicist based at UCL. Since 2014, he has worked within the Event Horizon Telescope team, developing and performing supercomputer simulations of black holes and horizon-scale black hole imaging, and he'll be telling us what those words mean tonight. If you look at Ziri's bio online, you'll see he's won a bunch of prestigious academic awards, including 2 breakthrough prizes for physics. But what his online bio doesn't tell you about is his equally successful underage swimming career. I'm sure astrophysics is glad that he never went on to become an Olympic breaststroker and looked up to the stars instead. Without further ado, I'll hand you over to Dr. Ziri Younsi.
Thank you so much, Sarah, for that really kind introduction. And good evening, everybody. And thank you so much for this opportunity to speak with you all today about a topic which I'm really passionate about and I've been working on since I was a PhD student, actually, back in 2008 is when I started looking at black holes and what they would look like. And back then, we didn't know what they would look like. And today, actually, since 2019, we have pictures of black holes. And I was very lucky to work in this project, the logo of which you see in the bottom left of the screen, called the Event Horizon Telescope Project. And just to say that I'm also a UKRI Stephen Hawking Fellow, so my grant funding comes from there, and they enable me to do the science that I'm going to be talking about today. So I'm going to jump straight in because we've only got 15 minutes, and there's so much that I want to tell you. And the first is about a few basic questions. And actually, there are a few key points that we need to address when we want to image a black hole, and you can roughly divide these into 4. So we want to start by asking ourselves, what is a black hole first? So what does the theory tell us? And of course, we have to ask the big guy himself, Albert Einstein, since it's his theory of general relativity which predicts them. And then the next question we have to ask ourselves is, where should we look? Because there are lots of black holes and they vary in mass from a few times the mass of the sun to a few billion times the mass of the sun. And we want to make sure that we get a nice picture. So we want to make sure that they're close by as possible. We also want them to be as big as possible. So where should we look? The third question is, how can we see the black hole? How can we see it? With telescopes, presumably, but the technology until recently didn't even exist. So I'll talk a little bit about that this evening. And finally, the most important question as a scientist is, once we have that picture and we're able to scrutinize it, we have to ask ourselves, what does it mean and what can we learn from it? And so those are the 4 points that I really want to cover in this evening's talk. So let's jump straight in. And this is a basic anatomy of a black hole and its surrounding environment. So this is quite a simple picture, but actually it's quite effective. And so the dark region in the center here, this semicircular region, this is the event horizon. And I'm sure you've all heard of an event horizon. This is the region, the point of no return. So this is the region where nothing can escape, not even light. So once you cross this threshold, you're trapped forever within the black hole, forever causally disconnected from the rest of the universe. And this is what characterizes a black hole. And actually inside that black hole event horizon is the singularity. And I won't talk about that this evening, but if you have any questions, please feel free to ask me. There's a big problem, the fact that the equations have a singularity and that it hides inside the event horizon. But moving back outside, we have an accretion disk, that is swirly matter that you see outside. This is the accretion flow, which gets hotter and hotter as it moves slowly inwards towards the event horizon, and it radiates a lot of light across the entire electromagnetic spectrum, from radio waves all the way through to gamma rays. And this is the light that we detect from the black hole, because we can't see a black hole directly because it has this event horizon, but we can see the light from that matter which is orbiting around the black hole that radiates this light moments before it crosses the event horizon. And then finally, a lot of black holes, including the black hole that we will see shortly from the galaxy Messier or M87, have these big, powerful relativistic jets which can extend outwards in both directions. And they can extend further than the extent of the galaxy itself. That's how powerful these things are. Okay, and so the thing is, what I've just shown you so far, whilst it's accurate in the sense that it's a basic sort of taxonomy, it doesn't really describe to you what we see. And that's because black holes have gravitational fields so strong that they not only trap light within their event horizons, but they bend it. So we're used to light traveling in straight lines. That's the universe that we know. But black holes are something special, and they actually can bend light. So here's a quick movie that we made in the Event Horizon Telescope collaboration. And we just fired a light ray past the event horizon, which is the red circle. Now this light ray passes closer, and you can see it bends back on itself and is deflected through a large angle. If we rotate our field of view, what you're seeing, this blue stuff, this is space-time, and you're seeing more and more rays being fired past the black hole. And we're collecting these rays at a distant source, at an observer rather, sorry, which has a sort of CCD or a photographic plate. And if we fire many, many, many rays and we reach a sort of continuum limit, we can construct an image because each ray is like a pixel of an image. And we obtain this dark shadow characterized by a bright edge, which decreases roughly in intensity as 1 over the distance squared. And this is what we call the black hole shadow. But of course, in practice, black holes aren't perfectly circular. They do have spin, and the distribution of matter around them, which produces this light, is not uniform. It's actually highly nonlinear and non-isotropic. And so actually we have to work a little bit harder to construct a real image. And so in the next few slides, that's what we're going to do. We're going to try and build up a picture and increase the complexity of this distribution of the matter around the black hole until we reach something that's very similar to what we actually find in nature. So let's do that. So first things first, we should say Hollywood had a few cracks at this. And one of the most recent ones is actually in the film Interstellar in 2014, which was a wonderful film, very exciting, a wonderful take on the notions of space and time and relativity and so on. And they showed in one part of the film a journey to a black hole called Gargantua. And this black hole has an enormous accretion disk. And this is the accretion disk from the film. It looks spectacular, but as a scientist, I'm afraid to say it's not entirely accurate. And that's because it's uniformly bright. It's bright on both sides of the image, when actually this black hole is spinning. So the side which is approaching us should appear brighter because it's relativistically beamed or Doppler beamed into our line of sight. And the receding side, which would be the right-hand side, should be dimmer. And actually, the first proper calculation of this was done by someone called Jean-Pierre Luminet in 1978. And he did this on really old supercomputers back in the day. You know, like a wristwatch would be more powerful than these computers. And each one of these points, which was on, India ink on photographic plate, was an independent calculation. But as you can see, the left-hand side of the image is bright because the black hole is spinning towards us, and the rear side is dim. But more than that, actually, is you see that the image looks a little bit warped, like there are bits folding up and down. And that's due to the bending of the light. So if you imagine now, you have a photographic plate here in green, and we put a disk around the black hole. Now, if we consider light being emitted from that disk, that accretion disk around the black hole, the gravity of the black hole in the center here bends the light, which would normally never reach us, into our line of sight, and so we can collect it. And actually, light can orbit the black hole multiple times. So if you were to make an image of this, what you would see, instead of like looking at a disk edge on, and it would look like a thin wedge if you looked at the disk edge on, you see something like the rear side of the disk folding upwards towards you, and the underside of the disk folding towards you. And that's what you see here, these two lobes at the top and the bottom of the image. So this is a thin disk. The distribution of the matter hasn't changed, and yet the image makes it look like it's something very, very different. And this is important to note. And actually, with a black hole, it's so extreme, the gravitational field, that if you were to stand near the event horizon, light from the reflected off the back of your head would orbit the black hole multiple times and go back into your eyes. And so you'd see multiple images of the back of your own head. So light does very strange things, and it's important to keep this in mind. And so what we can actually do is we can build more realistic models. So this is actually a spinning black hole, and it's just background stars that are painted on the sky here. And you see the shadow here in black. And the shadow is everything that is trapped by the event horizon, basically. And you see that there's just a dark center and then stars. But in reality, of course, there'd be matter swirling around that black hole. And so if we do that and we fold that in, then you see something like this, which was actually on my introductory slide. And what you're seeing here is this matter swirling around the black hole, and the stuff on the left that's approaching us is very bright because it's in our line of sight and it looks really hot. And you see these thin wisps and turbulent eddy-like features, and this is due to magnetohydrodynamic turbulence. So we simulate this stuff on a computer, and we perform special calculations which calculate how light moves around the black hole and through this plasma, and this is how we construct these sorts of images. And so we can go one step further and we actually make movies. So here's a static frame of a black hole, and we can actually even look at what the black hole would look like at different viewing inclinations. So from above, it looks like just a ring, but edge on, you see the underside and the rear side warp up. And then when we go back to the bottom pole, again, edge on, you see it's just circular again. Now we go back into the equatorial plane, and we're going to fly around this time. And as we fly around, you can see this distribution of turbulent matter. And so the matter, it doesn't have a coherent structure. It is quite turbulent, and it varies in space and time. And this is actually quite similar to what we see in nature. Okay. And so the next question is, we have an idea of how to build these things on a supercomputer. So we have models now. And the next question is, we have a model. Now let's try and confront that with some observational data. And so we need to decide where to look. So we could look in our own galaxy, and we could look further afield. And actually, there are two main candidates for the EHT, and that's Sagittarius A star and M87. Now, there are three things in general that we need to consider. We need to consider the mass of the black hole, its distance from us, and the various visibility conditions which affect our ability to make a good image. So in terms of mass, Sagittarius A star is 4.6 million times the mass of the Sun, but M87 is over 1,000 times more massive at 6.5 billion. Distance-wise, M87 is more than 1,000 times further away. So if you look at the ratio of the mass to the distance of these two objects, so the angular size on the sky, they're roughly the same. But in terms of visibility, you see that M87, the only major thing we have to contend with is the atmospheric effects in our own atmosphere. But for Sagittarius A star, in addition to those effects, we have to worry about the interstellar medium scattering and the time variability, because the black hole is 1,000 times smaller, so timescales vary 1,000 times more rapidly. And what that means is it's very hard to take a clear picture. And because we live at the edge of one of the galaxy's spiral arms, we have to look through the plane of our galaxy in order to take this image, which is very challenging indeed. And this is why so far we haven't published an image in the EHT. But I should say that actually we'll see an image of a black hole, of the black hole in our galaxy very soon. I can't say when, but very, very soon. And so far we've taken the image of M87, and that was the target for the Event Horizon Telescope collaboration. And that's the image that we've all seen. And so the question is, how can we see the black hole itself? And as it turns out, when you perform these simulations of matter accretion onto black holes, which is what I'm showing you here in this movie, once the matter winds up enough, it powers this bright jet in green, and this matter becomes turbulent and wispy. And if you zoom in onto an atomic level, or rather I should say a microscopic level, you see lots of magnetic field because it's highly magnetized. And you have lots of free electrons because it's a plasma, it's very hot, and so everything's separated into a soup of charged particles. And these electrons gyrate around these magnetic field lines. And as they gyrate, they radiate a lot of energy in the form of radio waves. And it's actually these radio waves that are produced by the black hole that we can detect. And so, how do we do this? Well, there's actually a specific frequency to tune into for the black hole. And it happens to be 230 gigahertz, or 1.3 millimeters. Which is actually very, very short, but actually long enough that you can measure it. So actually, as far as wavelengths goes, actually really long. And so you have a telescope, you point it at night, of course, at your source, and it turns out that, roughly speaking, the resolution of the telescope is proportional to the ratio of the size of the telescope to the wavelength. So you can either increase the size of your telescope, or you can decrease the wavelength. So you can build bigger and bigger telescopes, but unfortunately, in the case of NIO and Green Bank, this happens. So there are mechanical, engineering, and geographical limitations. And it also just costs a lot. And you can push to shorter and shorter wavelengths. So in the next few images, what you'll see is an image at one wavelength, and you don't see very much. It's self-absorbed. And as you decrease the wavelength, you'll notice the image gets brighter, and you can see closer and closer into the center. This is the EHT's frequency now of 230 gigahertz, or 1.3 millimeter wavelength. And in the future, we'll be able to make images like this, which are even sharper. And you can see this left approaching edge. And so the shadow of the black hole is more clear. And so ultimately, what the EHT does is it's very, very, very sensitive instrument. And to give you a sense of the scale of this, the size of the moon a full moon rather at night, is around 1/2 degree on the sky. Now, the shadow of the black hole in M87 has a diameter of around 40 microarc seconds. That's 1/90 millionth of a degree. And it turns out the EHT has a resolution of a factor to be better than this. And so what the EHT is actually able to do is do something incredible and actually be able to resolve something of the order of the size of an orange on the surface of the moon from here on Earth with your naked eye. That's the resolution that the EHT achieves. It's an unprecedented resolution. And so what is the EHT? It's actually a network of radio telescopes. And here are a few of them in this short movie I'll show you. So we have 7 or 8 that were used at the time to take the image. And now, since 2019, there are actually more and more being added every year. But these are the main ones. ALMA, as you can see here in Chile, is the most important one because it's the most sensitive, it's the biggest. And so as the Earth rotates, these telescopes point at the black hole and they record data. And I've been to this one in Hawaii, it's beautiful. And finally, the South Pole Telescope. And so everything's recorded with these telescopes. And here's the array as it was in 2017 when the data were recorded, which we published in 2019 in this now famous image. And so just getting towards the end of the talk, what we do in the end is we collect this light, that was produced 55 million years ago. It travels this enormous distance, and it eventually makes its way to us here on Earth, but it passes through our atmosphere, and it's received not just at one telescope, but actually at multiple telescopes. And the precise time of arrival of this radiation, actually of these radio waves, is recorded across all telescopes in the EHT array using hydrogen masers or atomic clocks. And you have to have a precise timestamp because we have to use VLBI technology, or very long baseline technology, to stitch it all together. And in so doing, we're able to create a virtual image, a virtual telescope, which can create an image of the order of the size of the Earth. And so what we've basically done is create a virtual telescope, and it's networked together to create a telescope the size of the Earth. Okay, and so one last thing before I conclude is that actually we published the result just last month, and it didn't gain the same kind of media furore because it's just a quick update, but it's actually, we looked at the polarization of the light. So what the polarization does is it tells us, it's like wearing polarizing filter sunglasses. It filters out certain parts of the light, and it tells us a lot about the magnetic field structure. And we have an updated image, and you see these swirly features. They actually tell us where the magnetic field in that hot plasma that's falling onto the black hole in the center of the image there is going. And so what have we learned so far? Last 2 slides. So we've learned actually that this black hole, which is the dark region in the center of the image, is larger than our entire solar system. It's enormous. We found out that the mass of this black hole is of the order of 6.5 plus or minus around 0.7 billion times the mass of our sun. That may not sound impressive, but this is a very far away black hole, and our measurements before weren't as precise. And this time we've used Einstein's general relativity to constrain this, and it's consistent with previous constraints. We can actually test other solutions. So some people think, oh, there aren't any black holes, there's wormholes, or there's boson stars or whatever. Well, it turns out it isn't a wormhole, it isn't a boson star, because the size of this bright ring is not consistent with those models. So we can rule out a lot of models and theories. And we see a lot of variation from day to day. And so actually the size and shape of the shadow enables us to test the theory of gravity and therefore test Einstein's theory and where it breaks down. And we're not quite there yet, but in time, as these measurements improve, we'll be able to do this. And so there's a lot of ongoing and future work, but the number one thing we're doing right now, and it's all hands on deck, is taking a picture of the black hole in our galactic center, Sagittarius A star. And I just want to conclude by saying that this is not the end for this work. It's pioneering work, and it's just the beginning. And in time, we'll have images that are very, very sharp and precise. And that's it. Thank you very much.
Thanks very much, Ziri. That's super interesting. And I'm sure your decisions to visit these telescopes around the world are not based on the ideal holiday destination either. Great. So keep your questions coming in through the chat. I saw a few coming in there. We're going to have a short break now for you to grab yourselves a drink. I've got mine here. And in that time, I'm going to talk with Divya. We're going to bring Divya onto the stage/screen. And Ziri, I've just got a few questions for these guys. They're kind of random questions, icebreaker type things. It's going to be like an awful first date for everybody. And we'd love for people in the audience maybe to participate a little bit too and let us know your answers to some of these things. So my first question is, this is Pint of Science. ideally, we would love to be in a pub, but we're not. If I was buying you around, what would I be ordering? So, Divya, I'm heading up to the bar. What am I getting you?
I actually don't drink, so I'd ask for a ginger beer.
Good choice.
And if it's after the talk, a pint of Strongbow. If it's before the talk, then probably just a Diet Coke, please.
Whereas you're after the talk, so we'll go for the Strongbow for you.
Definitely.
Okay, so as of yesterday, 17th of May, we can now have 6 people indoors. After Pint of Science, you guys decided to go for dinner. You can have 2 guests each. The classic dead or alive, famous or not famous. Who's your 2 dinner guests? Ziri, you can go first this time.
Oh gosh, putting under pressure. I hadn't thought about this one. Dead or alive? Now that's the key thing. The thing is, to be honest with you, I sound really boring, but we had a year of lockdown basically, and there's a lot of people that I've really missed. So I would definitely have to bring 1 or 2 close friends and family along. But I guess some great scientists from the past I would love to talk to, some great philosophers. I won't mention any and give away my sort of political or socio-political leanings, but I think for the time being it would be close friends and family.
Divya, are you going to default to the same?
Yeah, I would say if it wasn't close friends and family, I would say Carl Sagan. And I think he counts as 2 people. Just based on the conversation, I think. And I'd be happy to just listen to 2 people's worth of conversation from Carl Sagan.
You're not inviting anybody else. You're just going to tell everyone else. You can, you know what? You can sit at a table of 4 over here, and me and Carl will just have one. Great. Super serious question. If you could have one superpower, 2 great scientists, what would it be? Divya, I'm going to put you on the spot first.
This is going to be super geeky. Just being able to survive on another planet would be a superpower, I think. Don't need any oxygen and don't need any radiation protection, and leave me somewhere and I'll be pleased.
Do you know what? As an astrophysics talk, I would be disappointed if you said anything else. Great answer. Ziri.
So
you can't have the same. You have to have something else.
No, that's a great answer. I mean, to be honest, if you asked me 10 years ago, I'd say the ability to travel, to instantaneously transport myself to places or whatever. Actually, nowadays, I would say I would love to be able to speak every language and just be able to communicate with everybody in their native tongue. It would be the most incredible power to have. And I've learned that just living abroad in different countries, and you just realize it's only when you speak to people in their own language that you really, connect. So that would be my power.
That's super cool. Do you know what? I didn't expect either of those. I thought, there's the usual flying, invisibility, read minds. That was really good. Thanks, guys. So you touched on travel a little bit there. So I like this one. When travel opens up again, and we're assuming 0 COVID, so not the if, when, buts, we're stopping, COVID's gone. We're going to make this on Earth because I know how much you both would love to leave this Earth and see what's out there. Where's your ideal next travel destination?
I'll say, okay, this is kind of a cop-out, but I miss the UK, so I would go back to the UK. And nowhere specific, I think just anywhere. I miss Waterloo Station. I mean,
I don't think anyone has ever missed Waterloo Station.
Just take the train somewhere and have an exciting day. That's something I miss.
For me, I'd love to go back to a place I went to a friend's wedding many years ago in Sicily, a little town in that region, and just enjoy yummy food and good weather and a few relaxing days. So not so exciting, I'm afraid.
Bit of a contrast. And Divya, you wouldn't know, but we've had the classic London rainy weather this week, which we haven't had for a while. So some of us forgot. I was with some Irish people yesterday, and Ireland's been sunny and the UK's been rainy, and we said this is why we moved over here, was to get away from it. No. Okay, so I have some quick fire. We're about to restart, but I do have a quick fire round, so I'm going to throw these at you very quickly before we get going again. I'm going to alternate these just so that we get done. So Ziri, Coke or Pepsi?
Coke.
Divya, cats or dogs?
Both.
I'm going to let you go just out of time. I'd force you otherwise. Ziri, are you a morning person or a night owl?
Night owl.
Divya, what's your favorite season?
Fall.
Autumn for our UK listeners. We all know what that means. And the last one, I'm going to make you both answer this. A Jaffa cake, is it a cake or a biscuit?
Cake.
I've never had Jaffa cake, so I can't say.
Okay. You need to come back to London. You need to get yourself a Jaffa cake. And on that note, thank you very much for entertaining us and hopefully the people at home through that. I haven't seen the chat. I'd love if people gave some answers to those questions yourselves. And we're going to get going with our second talk. Let's get back to the science. Great. So you've had a brief introduction there to our second speaker. Unfortunately, she started with her fun facts instead of her science, but she'll get to that now. So our second speaker tonight is Divya Persaud. When I first read Divya's bio online, I told the Pint of Science team that I thought she was the coolest person I've never met. No offense to Ziri. Divya is an alumna of the NASA Academy. She's finishing up her PhD at UCL and has already secured a postdoctoral scholarship with the Europa Lander team at the NASA Jet Propulsion Laboratory, which if you're in any way nerdy, all of those words sound super cool. Not just a setter scientist, Divya also has a degree in music composition and produces art in the form of poetry and music. In her own words, Divya hopes to be the first cellist on Mars, which, if she had a superpower, would be pretty easy for her. We're lucky to have her here on Earth with us tonight. Divya, the floor is yours.
Thank you so much for that very generous introduction. Can you see my slides? Yeah, perfect. Thank you. So today I'm going to give you a brief tour of a little place called Gale Crater on Mars in 3D. So to start out, kind of why do we care about Mars? Mars is sort of our sibling planet. There's a lot on Mars that reflects what happens on Earth. So for example, on the left, there are volcanoes on Mars. The middle column, Curiosity rover has encountered mineral veins that are a lot like the mineral veins that we get that sort of form in water in warm environments. So we sort of have these ingredients of heat and chemistry that on Earth really support life. So we have the ingredients there, but do we have the evidence of life? And that's kind of the question mark of, how do we find that evidence from here on Earth, right? So as geologists, I'm a planetary geologist. Geologists' work is very hands-on. So here I have some pictures of what geology kind of means. It means people going out in the field and taking samples and looking at things under a microscope and taking measurements out in the field or doing sort of chemical tests in that environment, or even standing outside and looking at rock formations, taking measurements, drawing, walking around them, touching them, looking at the textures. And all of this adds up to the story of Earth. So here's a picture of something called a stratigraphic column. And this is what these people on the left are building. So you can sort of see the drawing that they're building. They're building essentially a time series or a sort of little story of what's happened in this area. And all of these observations and measurements go into that story. So this diagram shows different layers in the rock, and time is basically going down. So this is a little sort of, I call it a time capsule or a time machine, the way that geologists sort of reconstruct what's happened. And a lot of that work goes towards, was there a lake here, an ocean? How did that ocean change? Was there life? So for Mars, how do we do that, right? We can't go and touch things and see things and walk around them. But of course, we have our little geologists called rovers. So on the left is Curiosity rover, which I'll be talking about today. And on the right is Perseverance. So these rovers are pretty much the same. Perseverance is a little sort of updated. And they have lots of instruments on them. And they basically can do what a geologist can do out in the field. And not just one geologist, but a team of geologists. So on their little heads, they have cameras. There are tons of cameras on these rovers. They have little chambers where they can take samples and explode them and see what they're made of. There are lasers, there are different types of cameras to look at chemical composition. And of course they move. So they're getting an idea as they move of the geology around them. So here's a little picture of Curiosity. You can see all the sort of different types of mechanisms on it. So it's basically a walking laboratory, doing as much as it can for us geologists back here home. And here's just a little image of some spectra. So these are from lasers fired at different rocks to see the sort of reflectance that they give, and that can give you composition. So that's a lot like what a geologist might do if they take a sample back to their laboratory. So it's not just someone looking around, it's really getting to experiment. The problem with rovers is that there aren't that many of them. This looks like a lot. These aren't all rovers. Some of these are stationary landers that have landed on Mars over the past few decades. And so if we want to build a really big picture of the story of Mars, rovers fill in a lot of detail, but they're really, really local detail. And even when you zoom in on, for example, Curiosity on this map, it's not that big of a spot. It's actually a really, really tiny spot. So even if you had humans on Mars, if you sent me to Mars and I walked around for 9 years, which is what Curiosity rover has been doing, I still wouldn't really see that much, and I would be walking really slowly. I would see basically what's in my field of view, and there would only be so many samples I could take with the energy that I have. So there's a lot missing from the Mars story. And how can we fill that out? We can use satellite data to do that, actually. So here's an animation of a satellite that's orbiting Earth. And you can see there are also lots of instruments on this. There are cameras. A lot of these satellites that are sent to planets are basically like flying geologists. They can't do experiments, but they have special instruments that can remotely sense all sorts of details about the surface. The problem with a flying geologist is even with all of these tools, the satellite looks straight down. And here's a really great animation of a satellite that goes around Earth. And that's the type of image that you get. It's huge. And that means you get a lot of information, but it also isn't as high resolution as you would get if you were standing there or if you were a rover. It's also looking straight down. So geologists use maps, but we use maps in a way that, we walk around, we see things in a sort of human way, and then we contextualize that with a map. We put it out into a map. And this is sort of the reverse. We are getting the map, but we don't know the context. We don't know what it would look like if we were on the surface, looking like a person staring out at the horizon is just straight down. So we lose a lot of information. And so for geologists like me to do our work, we have to try to find ways to make this a lot more understandable for us. And one way we can do that, and this is the focus of my PhD, is using 3D imagery. And I'll just focus on images today. So this is a way that we can almost simulate that field research environment for ourselves. So first of all, how do we even sense in 3D? 3D sensing is really important for us as scientists. And we sense in 3D not only with our eyes, but our ears and touch. And so with our eyes, it works because we have two of them. And each eye is actually capturing a different image of our world than the other eye. And that separation between our eyes is why. And say we look at a tree and we're getting these two different images of that tree, very slight. And if our brains know where the sun is, if the brain also kind of knows the material of the tree, and some other factors, sort of, how tall we are, where we're standing, our brain can calculate the third dimension from this. And that's how our ears work as well. So a computer kind of does it in the same way. So if you give a 3D processing software two images that have been taken from different eyes. So say you have a satellite going around Mars, and it takes one picture on one orbit, and then it takes another picture on another orbit, and they're slightly different. And you tell the computer, this was where the sun was in the sky. This is how, this camera works. This is the distance of the camera from the surface. It can solve for the third dimension. So it's a lot like how we do it. And it's actually based on how humans sense in 3D. So for my PhD, I've put together a lot of 3D images from various cameras in orbit around Mars. We have so many cameras in orbit around Mars at different resolutions. And it made up these big 3D maps of the exploration site of Curiosity rover. And in these different resolutions, and I've tied them all together so we know where everything is. Because when you take the highest resolution images, they're very limited. So you want to be able to get as much geology as possible. So I'm going to show you what that looks like. And I'll give you a little tour of Gale Crater. So this is the 3D data in a nice visualization suite. So this crater was formed by a big impact. And then there's this mountain in the middle. And this mountain is called Mount Sharp. We don't know how it formed. There have been theories about volcanism or sediment transport or water forming it, but we don't really know. And this has been a big question for Curiosity rover. And the central mound is this bigger mountain that it's sitting on. And we don't know how it formed, but we can use the different tools that we get from the rover to explore this, but also images like this. So you can see there's a lot of diverse sort of shapes and textures in this crater. There's been a lot of different processes happening. For example, here is evidence of water flow in Fara Vallis. So this was a river channel that was once active within a lake. And here's another river channel that I'll talk about in a minute called Sakarya Vallis. And this was also really active. And this was filling into the lake as well. And that cuts into the central mound. And this is finally showing the Curiosity rover traverse as of yesterday. So that's showing in white. And it's slowly going up the central mound. And as it goes up, it's seeing the layers that cut through this central mound. It's going back in time as it looks at the rocks, but it's going more recent in time as it's ascending. So this is sort of the story that we have of Gale Crater from rover science. And this is from the Curiosity rover team. So we have the big impact. Then we have all the sort of groundwater that existed probably 2 billion years ago, filling in these cracks. And it probably filled in the crater. And then rivers also flowed into the crater and formed a lake system. So as that lake rises and falls and rises again, we get these beautiful lake sediments. And that's what Curiosity rover has been encountering for the past about 9 years. But eventually this water runs out. Mars gets dry again. There's still water underneath the surface, but not on the surface. And sediment starts to blow in and make these huge dunes. And then eventually these dunes also start eroding away. And this is sort of where we don't know what happened to form Mount Sharp. We think it eroded away, but we don't really know the mechanism here. And eventually you get cross-cutting of all these lake sediments and also dune sediments. And then you get that water actually upwelling and forming mineral veins. And then modern day, it's just dry, and that's where Curiosity rover is. So how can we actually tell the story more exactly? So I showed you a stratigraphic column earlier. So we have one of what Curiosity rover has explored so far. We don't know what's above it. We don't know what's more recent. So one way we can do that is look at layers higher up than where Curiosity rover is, and that's been what my PhD is. So this is Sakarya Vallis, which I showed earlier. And you can see these really beautiful exposures of these layers. And it's really amazing. So this imagery is the highest resolution imagery that we have that isn't from rovers. So this is about the biggest thing you could see would be a 25 centimeter rock, which is actually pretty amazing for a satellite. And so if we can compare those layers to models of formation, then we can actually figure out what's going on. And one way we can do this is actually look at it as if we are geologists in the field, as I mentioned. So we can use special software that has geology tools to measure out these layers and their orientations and their relationships, and take notes on their color and other sort of textures and other factors about them, and consider, okay, well, what does that tell us about the environment that formed them? So this is sort of the idea of what it produces. This is some of my later PhD research of building up that little story of just this little area and seeing how it fits into a bigger story. So that's sort of a summation of what I've been doing. And Curiosity rover is slowly heading up the central mound. And this is, again, the highest resolution imagery. And it's going up this other channel called Geddes Vallis that also formed from water flowing down this mountain. And it'll start to encounter some of these layers that I've been looking at. and sort of fill in this bigger picture of, okay, how did this thing form? And then the mission will end in about 2 years. So here's a little comparison just to bring it home. In the upper right is the rover image. This was taken, I think, yesterday. And the bottom left is what geologists using the software might actually see at this exact spot. So this is really useful data, and it's a way that we can almost touch the surface of another planet. And so thank you.
Great. Thanks very much, Divya. It's super interesting. Again, just 2 really great talks from both of you. So Ziri's going to come back, and we're going to open the floor to a Q&A. So I did see lots coming in from our YouTube comments there. So the first question is, that magnetic field photo of the black hole is amazing. So this is headed towards you, Ziri. How long does it roughly take to get that level of detail from the images?
Great question. And it took us 4 years, basically, to get to that point. Quick answer would be, we had the data recorded in 2017. It took us 2 years just to sort of to calibrate it, to do lots of various things like fringe fitting, because these are radio waves. So they actually they're not like discrete photons, they're wave patterns. We have to fit those patterns together in a process called fringe fitting. It has to be done on supercomputers. So all of that data has to be shipped from the telescopes to central locations where that process is done. Then once those fringes are found and we know how to stitch it together using the atomic clocks, then you have to do several other stages of processing to actually reduce that data from several petabytes down to something which it turns out to be a few megabytes. And then once you have that final data set, then you have to construct an image from it, because you record everything in what's called Fourier space. So that, just to get an image without polarization, took about 2 years. Then it took another 2 years to get the polarization, because polarization has 4 components instead of 1. So yeah, 4 years.
So the next question is, when will I be able to explore Mars on my VR headset? That's a great question.
That is a great question. I'll say people are working on it. It's so there is actually a team. So part of the Curiosity rover team of geologists use VR to plan ahead for the mission. So what they do is they put all of the rover images into an environment with all of this orbital data and say, like, we want to drive here and here and here. And so it's pretty cool. So I think they're working on trying to make that publicly available. But yeah, there are a lot of people who want that really badly. And so it's not people like me who do it, but yeah, they're working on it.
Cool. Ziri, what happens inside a black hole?
Great question. I wish I knew. And so does every other scientist working on black holes. I can venture a guess. So inside the event horizon, a lot of people say, oh, you'd be destroyed, you'd be, shredded into your fundamental constituents. Well, actually, it depends on the size of the black hole. If the black hole is the size of this one in M87, so 6.5 billion times the mass of the sun, it'd actually be quite comfortable there. Gravity isn't actually super, super strong, or rather tidal forces are not super strong. So you wouldn't be stretched apart. What really happens, we don't know, because you enter what's a realm of what we call quantum gravity, and that theory doesn't exist yet because gravity isn't reconcilable with quantum mechanics. But the gravity needs to be understood on a quantum mechanical scale in order for us to understand what happens at and inside the event horizon. There are people trying to understand, but we know that the theory breaks down. We know that Einstein's theory breaks down because of the singularity. So what happens inside there probably isn't predictable using his theory. And so it's quantum gravity that will point us in that direction.
A surprisingly simple question, but definitely not a simple answer. Back on Interstellar, is there a way of getting the Curiosity to take more chemica, I can't pronounce that word, measurements, even as sampled as alkaline or acidic in the future?
Yeah, so Curiosity has a lot of laboratory sort of instruments. So it can get the composition of, say, a mineral in a few different ways. So it can explode it. It can take spectra of the gas from exploding it. It can use lasers. There are a few other ways. So you can actually figure out if something is acidic or alkaline from that. I mean, that's actually really, really important for looking for environments that were habitable, because you want to make sure that certain chemical reactions are happening. So that's a great question, and absolutely, and that was one of the priorities for Curiosity rover and for Perseverance as well.
Thanks. Another big question for you, Ziri. What would happen if two black holes ever collide?
Well, someone asked, I think someone partially answered that for me in the comments, but so we do actually detect black holes colliding, or rather, actually, just to be more precise, we detect stellar mass black holes colliding, so black holes which are a few times the mass of our sun, and we detect them using gravitational waves. So LIGO Virgo actually published a result. The event's called GW170817, and they've published events since. So they're mergers of black holes and of neutron stars. And what happens is, as they collide, they radiate a lot of their mass energy in the form of gravitational waves. These aren't like typical electromagnetic waves. These are actually ripples in space-time. Space-time is Einstein's geometrical fabric of the universe. So we live in space-time. Space-time is our reality, and gravitational waves are ripples through reality. And we can actually detect them using extremely precise laser interferometers, which is what LIGO and Virgo do. And so what we see is, or what we infer rather, is that as they collide, the horizons merge and they eventually become one black hole, and it's not spherically symmetric. They wobble, and then that wobble dissipates the rest of their energy until they're perfectly spherically symmetric again.
Awesome. Just a comment there. Thank you for your great talks.
Thank you.
And yeah, I agree with this. You know what, Divya, you do have one of the coolest PhD projects that most of us have ever heard of. When will Curiosity reach the areas that you've been studying? I have some sound issues. I don't know if that's me. Just
sorry about that. I have traffic outside, so I muted myself. Thank you so much. Yeah, it's so much fun. So Curiosity rover is basically at the very bottom of the layers that I'm studying. So the valley that I'm looking at is actually about 30 to 50 kilometers away. So I'll never get there. It's way too dangerous for it. But the layers actually extend throughout. So as of the past 2 months, it's gotten to the very base of the layers that I'm studying, I think, just based on elevation and some other inferences. So that's pretty exciting. And it will continue to go up basically through this and fill in a lot of detail. So very exciting. I didn't expect that at all. I just found this place interesting and then found that out.
As an academic, there's that whole thing of, well, in the future, I guess that's where we can go. So I don't think I'll be able to pronounce this word either, but was the Arecibo telescope part of the EHT array? And are there plans to rebuild it?
It wasn't. I know exactly which one it is. It's in the film Goldeneye, if that means anything to anyone at the end. And sadly, no, there are no plans to rebuild it. And in fact, it's sad that it fell apart because it fell into a state of disrepair, and that's why it happened. It could have been salvaged. But as sad as it is to lose the Arecibo telescope, there'll be bigger, better telescopes built in the future. And so I'm just trying to be optimistic. Let's look forwards. There are great things on the horizon.
Great. And this one's coming back to you, Divya. So does Curiosity have a depth measurement as it ascends? Can you fine-tune the satellite images measurements, or are the images accurate enough regardless?
That's an amazing question, because it's one of the biggest problems in planetary science is where something is. So I mentioned doing all of this alignment of data, and that's because we don't have a GPS system at Mars. We don't know exactly where something is. We don't have Google Maps. And that means when you land a rover, you kind of don't know. So if your best resolution is limited to 25 centimeters, which is pretty good, but you have a little rover and you don't know exactly where it's going to land, it's going to take you some time to actually figure out where it is. So luckily, Curiosity rover's been driving for 9 years. So we've found a lot of ways to refine where it is. So it's a bigger problem for previous rovers. So that's sort of the latitude and longitude, but also sort of the depth. So the best sort of altitude we can get is from the 3D data that I sort of make. So it's a bit complex. It doesn't really provide too much for what I'm doing. It's more like if Curiosity rover measures a 6-meter outcrop, what does that mean for me, rather than the exact location of that outcrop. So yeah, that's actually a really deep question and something that we're still trying to solve.
Cool. So this is going to be our last question for the night, and we're putting it out to both of you guys. So exploring Mars, AI robots and their limitations versus sending humans and their superior abilities, but with cost and risks and moral issues. What are your views?
I'm happy to go first. Yeah, that's also a good question. That is the eternal question for a geologist like me. What rovers sort of lack and what we could do pretty easily just by sort of walking around. And it's hard because sending someone, you need so much protection. You need to make sure that that technology is tested for ages and ages to make sure it won't fail, because you're dealing with human lives. So in terms of science, like, I'm happy for rovers to do my job. Like, we're finding other solutions, but we're sort of hitting a limit of like how much we can do. Cameras won't get that much better. And even if they do, it takes a really long time to get them to space. So I'd love to see planetary geologists doing work on Mars, but it is difficult. And as you mentioned, like, there are moral issues as well of like disrupting rocks. Should I really be going and like taking a huge sample and exploding it in a laboratory? And it's already sort of an ethical question of, should Curiosity rover be shooting lasers and that kind of thing? Should we be modifying the environment? And that comes down to like space law and space policy and sort of way above my pay grade. But I'd like to see ethical and responsible human exploration, but I'm perfectly happy with my little pictures on my screen for now.
Your superhero power might help with some of the risks as well, if that ever happens. Ziri, do you want to contribute?
Oh gosh, I think Divya gave a fantastic answer. I can't really add anything there other than I think it's inevitable that eventually we will be there. And so yes, Divya's answer about all of the ethical implications of human exploration. It was always my dream, actually, since growing up, that the next step beyond the moon was Mars. And for me, it's just it'd be wonderful to see that in our lifetimes.
I think that's a great way to tie up the show. So thank you very much to our two speakers, Ziri and Divya, for their fantastic talks and their questions and answers, both the science ones and my silly questions in the middle. And thank you so much to our audience for tuning in tonight, and for anyone who's watched the show back through on YouTube. For our audience, there is a chance to win some Pint of Science prizes if you fill out our feedback survey, which is going into the chat now and will be in the YouTube description. You can also tweet about tonight's events using hashtag Pint21 or @Pint of Science. If you enjoyed tonight's show, you can head to pintofscience.co.uk for the full program of events, and you can watch all the shows back on YouTube after their live streaming. Lastly, I just want to give a little shout out to the UCL Pint of Science backroom team for keeping the show going. I've been your host, Sarah Ledden. This has been Pint of Science. Thanks for watching. Enjoy the rest of your night.